All right, let's jump right in. We're going to break down what is, without a doubt, the most famous, the most important, and yeah, the most mind-bending experiment in all of physics. This is the one that really pulls back the curtain on what reality itself is actually made of.
And hey, it's not just me saying that. The legendary physicist Richard Feynman himself said that this one experiment contains the only real mystery of quantum mechanics. His point was, if you can really truly wrap your head around this, you've understood the absolute core of the quantum world.
So before we get to that big mystery, we need to set the stage. Let's start with the world we all know, the common sense world. In classical physics, things are pretty simple. They're either particles or they're waves. That's it. Now, the setup for this experiment is shockingly simple. You've got a source that shoots something, a barrier in the middle with two little parallel slits cut into it, and then a screen at the back that acts like a detector. The big question is simple. What kind of pattern is going to show up on that back screen?
Well, it really depends on what we're firing. If we shoot particles, think of them like tiny little marbles. They have to go through either the left slit or the right slit. You can't do both. And the result? Two clean bands on the screen, lined up perfectly behind the slits. Makes total sense. But if we send waves through, like ripples in a pond, something totally different happens. A wave passes through both slits at the very same time. This creates two new, smaller waves on the other side, which then spread out and interfere with each other, making a whole new, more complex pattern.
And that pattern has a name. It's called an interference pattern. See, where the peaks of the two waves line up, they get stronger, creating a bright stripe. But where a peak from one wave meets a valley from the other, they cancel each other out, leaving a dark stripe. So you end up with this series of many alternating bright and dark bands. This pattern is the undeniable fingerprint of a wave. And this whole idea has a pretty long history. Way back in 1801, a guy named Thomas Young did this exact experiment with light and saw that interference pattern. It was a huge deal because for centuries, people thought light was made of particles. This seemed to prove, once and for all, that light was a wave. But then, fast forward to 1927, physicists do the experiment again, but this time with electrons, things we were sure were tiny little particles. And you won't believe it. They got the exact same wave pattern. Now that was a huge problem. This result just opened up a whole new can of worms.
And this is the exact moment where our common sense world just breaks. We're now entering the quantum puzzle, where the rules we thought we knew are about to get very, very weird. So this gets to the heart of it. What is an electron really? Is it a tiny little marble behaving like a particle? Or is it more like a ripple, behaving like a wave? This experiment is designed to force it to show its true colors.
Okay, so let's get clever. Let's turn our electron gun way, way down, so we're only firing one single electron at a time. What happens? Well, a single little flash appears on the back screen. A tiny localized dot. It hit one specific spot exactly like a little marble would. So, case closed, right? An electron is a particle.
But let's keep it going. We fire another electron. Bam, it lands in a different spot. And another, and another. If you just look at the first few impacts, there's no pattern at all. It just looks like a random scattering of dots on the screen.
But what do you think is going to happen if we let this run for hours? If we fire thousands and thousands of these individual particle-like electrons, one by one, where are they all going to land? I mean, if they're particles, we should just get those two simple bands, right?
And here it is, the central mystery of quantum mechanics. As thousands of those individual particle-like impacts build up on the screen, they do not form two bands. They form a wave interference pattern. It's staggeringly bizarre. Each dot lands like a particle, but it lands in a spot that's dictated by a wave. They're all piling up in the bright bands and completely avoiding the dark bands. Now just stop and think about what this really means. Each electron is fired completely alone. There are no other electrons around for it to interfere with, so the only possible way for this pattern to form is if each single electron behaves like a wave, passes through both slits at the same time, interferes with itself, and then finally decides where to land on the screen as a single particle. It's like a wave of pure possibility that collapses into a single, real point.
So if your brain hurts a little bit right now, that's good. It means you're getting it. But believe it or not, it's about to get even stranger. Let's bring in the final, unbelievable twist. The observer effect.
This is the next logical step, right? Any good scientist would ask this. We want to know which slit the electron actually goes through. So let's set a little trap. We'll place a tiny detector right at the slits that will tell us, yep, that one went through the left. Or, aha, that one went through the right. We're going to peek.
And what happens next is just mind-blowing. The instant we turn on our detector to find out which path the electron takes, the interference pattern completely disappears. Gone. The electrons stop acting like waves and go back to behaving like well-behaved little marbles, forming two simple, clean bands right behind the slits. The very act of watching it changed the result.
Now, there's a scientific term for this phenomenon. It's called wave function collapse. Before we look, the electron exists in this strange smear of all possibilities, what physicists call a superposition. It's kind of going through the left slit, the right slit, both and neither, all at the same time. The act of measuring forces that wave of possibilities to just collapse into one single definite reality. Now, this is really important, so let's clear up a huge misconception. This has nothing to do with a person's consciousness looking at the experiment. The observer isn't a mind. It's any physical interaction that measures the particle's path. Even shining a single photon on the electron to see where it is counts as a measurement, and that alone is enough to collapse the wave and destroy the pattern. So, what does all this mean? Where does it leave us? Well, this one beautiful, elegant experiment reveals some of the absolute deepest truths about the very nature of our universe. So let's boil it all down to 5 core truths. First, wave-particle duality. Things like electrons can act like particles and like waves. Second, superposition. A single particle can literally be in many places or states at once, until we measure it. Third, the observer effect. You can't passively observe a quantum system. The act of observing it fundamentally changes it. Fourth, this leads to complementarity. You can know its wave-like nature or its particle-like path, but you can never know both at the same time. And finally, number 5, all of this tells us that reality, at its deepest level, is governed by probability, not certainty. And this is the most important thing to remember. These aren't just theories or wild interpretations. Physicists argue all day about why the universe is like this, but the results of the experiment itself are not up for debate. These are repeatable, undeniable, experimental facts. This is, quite simply, how our reality works at the most fundamental level. And that leaves us with one final, profound question to just let sink in. If the very nature of reality shifts and solidifies just because we measure it, what is the universe truly like when no one and nothing is looking?